Look down at the ocean. Not the simplified map they show you on the evening news, but the raw, unedited infrared feeds coming down from low Earth orbit. For generations, meteorologists have relied on a single fundamental number, 26.5 degrees Celsius. That is the baseline, the precise thermal trigger required for the ocean to ignite a tropical cyclone. But right now, the sensors are sending back data that our historical models were never designed to process. Vast stretches of our oceans are burning at 28, 30, and even 31 degrees Celsius. It might sound like a minor shift to the average person, just a few degrees. But in atmospheric physics, those few degrees represent a staggering volume of thermal energy, the equivalent of millions of atomic detonations happening silently beneath the waves, waiting to be released. Before we look at the exact mechanisms of what this heat is currently spawning, let's do a roll call. Drop a comment below right now. Where are you watching from, and what unprecedented shifts are you witnessing in your local weather? Whether it's sudden droughts, unseasonal storms, or shifts in the wind, we are tracking it. This channel operates as a global command center, and your ground-level observations are a critical part of this investigation. The textbooks sitting in universities right now will tell you exactly how a storm is supposed to grow. They will tell you where its physical ceiling lies. But the storms forming in these crimson waters are ignoring the rules. They are intensifying at speeds that blindside emergency managers. They are growing to sizes that cover entire land masses. And they are carrying a deeply unsettling message about the stability of our atmosphere. Something in the ocean has changed. To understand why these atmospheric systems are breaking historical bounds, we have to look past the surface. When mainstream weather reports talk about ocean temperature, they are almost always referring to the sea surface temperature. It is an easy metric to capture. Satellites read it in real time, painting daily weather maps in bright, easily digestible shades of orange and red. But the surface alone tells less than half the story. A tropical cyclone is, in the strictest terms of physics, a massive mechanical mixer. As its intense winds rotate across the open ocean, the sheer friction drags deeper water upward. Historically, this physical process acted as a vital natural safety valve. If a storm churned up water from 100 meters down, that deeper water was inherently cold. Once that cold water reached the surface, evaporation would slow, the updrafts would choke, and the storm's heat engine would be starved of its primary fuel. In meteorological terms, this is called upwelling. It is the reason why, for decades, massive storms would often weaken themselves just as they were trying to grow. They effectively drank their own poison. That safety valve is failing. What subsurface probes and deep ocean autonomous buoys are now recording is a profound structural shift in the water column itself. The heat is no longer just a thin, temporary film on the surface. It has penetrated 100 to 200 meters into the abyss. When a modern cyclone moves across these anomalous zones and churns the ocean, the water it brings up is not a cooling break. It is 29 degrees Celsius. It is pure, unadulterated fuel. Oceanographers quantify this hidden reservoir using a specific metric called Tropical Cyclone Heat Potential, or TCHP. It is not a simple temperature reading. It is a calculation of the total thermal energy stored between the surface and the depth where the water finally cools. The scale is absolute. Values above 90 kilojoules per square centimeter are considered highly dangerous, providing enough ambient energy to sustain a major hurricane. Right now, in key development zones across the global warm pools, we are tracking TCHP values repeatedly exceeding 120 kilojoules per square centimeter. When a developing storm taps into a reservoir of this magnitude, the fundamental dynamics of its life cycle change entirely. There is no cooling effect beneath the eyewall. There is no break in the evaporation cycle. The storm pulls heat, the ocean delivers more heat, and the engine runs at maximum thermodynamic efficiency, hour after hour. It does not run out of fuel because, relative to the storm's lifespan, the fuel supply has become essentially inexhaustible. It is no longer operating as a standard weather event. It has become a runaway feedback loop. And this deep water thermal battery is the precise mechanism driving the most terrifying atmospheric behavior we are witnessing today, the collapse of the time we have to prepare. That collapse of time has a specific, highly technical designation in meteorology: rapid intensification. For most of modern weather tracking history, a developing tropical system followed a predictable, almost linear path of growth. A tropical depression would spend days organizing into a storm, slowly gathering strength over open water. Emergency managers relied entirely on this linear timeline. It provided the most critical resource in disaster management, the window to act. The days required to issue warnings, board up infrastructure, and execute mass evacuations. The scientific threshold for rapid intensification was established to flag storms that deviated from this slow curve. Historically, if a cyclone gained 55 kilometers per hour in sustained wind speed within a single 24-hour period, it triggered extreme alarms. That jump was considered the absolute benchmark for dangerous, accelerated growth. It was a rare event, an outlier that forced meteorologists to sit up and pay attention. But we are no longer dealing with historical outliers. We are dealing with a completely rewritten baseline. When a modern storm positions its core over the deep, 120 kilojoule thermal reservoirs we just examined, the old metric of 55 kilometers per hour becomes completely obsolete. We are now routinely observing systems that detonate, there's no better word for it, gaining 100 to 200 kilometers per hour in sustained winds in that exact same 24-hour window. This is not growth, is atmospheric hyperacceleration. The storm does not gradually build. It explodes into a catastrophic force while coastal populations are still sleeping, operating under the fatal assumption that the threat is days away. To comprehend the mechanical violence of this acceleration, we must look at the benchmark event that permanently altered the meteorological record, Hurricane Patricia. Drifting over a pool of exceptionally deep, warm water off the coast of Mexico, Patricia's sustained wind skyrocketed, gaining an astonishing 209 kilometers per hour in a single day. The system consolidated from a moderate threat into a tightly wound 346 km per hour atmospheric buzzsaw. Patricia achieved this by compressing its destructive energy into a tiny, intensely efficient rotation. When you force massive volumes of rapidly rising, superheated air into a narrow column, conservation of angular momentum takes over. Like a figure skater pulling their arms enduring a spin, the tighter the core, the more violent the rotational velocity. This hyper-accelerated timeline represents the most critical vulnerability in human infrastructure today. The evacuation protocols of every major coastal city on Earth are fundamentally predicated on having 48 to 72 hours of actionable lead time. Moving hundreds of thousands of people, shutting down power grids, and securing critical facilities requires days, not hours. What happens when a storm approaches as a manageable Category 1, then feeds on a deep heat pool offshore and detonates into a Category 5 overnight? The terrifying reality of modern rapid intensification is that it strips away our physical capacity to react. We are forced to watch as the system transitions into a highly organized engine of destruction, moving faster than the mechanisms of human evacuation can possibly deploy. The ocean has changed the rules of engagement, and our civil defense systems have simply not caught up. When we observe a storm undergoing rapid intensification, our immediate and visceral focus is understandably on the wind. Wind is visible. Wind is what shatters glass, tears roofs from concrete foundations, and turns everyday infrastructure into lethal projectiles. But wind is merely a symptom. To understand the true destructive potential of these modern atmospheric anomalies, we must look past the visible chaos and examine the invisible architecture that drives the air. We must look at barometric pressure. Atmospheric pressure, in its strictest definition, is simply the raw weight of the air resting above a given point. On a normal clear day at sea level, the sky presses down on us with a weight of roughly 1,013 millibars. It is a baseline force of nature that our bodies and our buildings are perfectly calibrated to withstand. But inside the core of a developing cyclone, that baseline is violently erased. As superheated, moisture-laden air rises rapidly from the ocean surface, it creates a massive void beneath it. The warm, rising column of air inside the eye weighs significantly less than the colder, denser atmosphere surrounding the storm. This creates a severe localized deficit, an atmospheric vacuum. Nature abhors a vacuum. The lower the pressure drops at the surface, the more violently the surrounding atmosphere is pulled inward to fill the void. The relationship is entirely mechanical, almost clockwork. The greater the disparity between the low pressure at the center and the high pressure at the outer edges, the faster the wind must accelerate to bridge the gap. Pressure is not just a secondary metric, it is the absolute throttle of the hurricane's engine. Every single millibar that the pressure drops translates directly into a terrifying, exponential increase in sheer kinetic energy. For decades, meteorologists believed there was a firm physical floor to how low atmospheric pressure could drop at sea level. A highly intense, Category 5 super typhoon typically registers a central pressure somewhere below 920 millibars. That number alone denotes a catastrophic event. But the historical benchmark, the absolute limit of what we thought the planetary system could produce, was set in October 1979 by Super Typhoon Tip. When reconnaissance aircraft penetrated Tip's core, their instruments recorded a central sea level pressure of 870 millibars. That reading remains the lowest atmospheric pressure ever measured in a tropical cyclone anywhere on Earth, a record that has stood unbroken against nearly 5 decades of global observation. Tip's 870 millibars represented a staggering atmospheric deficit. The pressure difference was so vast, the void so deep, that the storm's resulting wind field expanded outward to cover an area wider than the distance from New York City to Denver. The deficit was so enormous it forced scientists to redraw the upper limits of what was physically possible. Yet, what haunts modern climate scientists is not the record Tip set, but the environment in which it formed. Tip achieved that terrifying 870 millibar floor over an ocean that was significantly cooler and held less deep thermal energy than the one we are measuring today. As the deep thermal reservoirs of the ocean continue to expand, absorbing unprecedented levels of heat, the theoretical floor for barometric pressure is falling away. Warmer oceans actively raise the theoretical ceiling for storm intensity, providing modern cyclones with far more room to deepen than they had 40 years ago. We are now entering a regime where the physics strictly allows for pressure readings well below the 870 millibar mark, pushing into a zone the models confirm, but our instruments have yet to verify. When storm's pressure plummets into these uncharted depths, the resulting inward rush of air generates wind speeds that push far past the boundaries of our current structural engineering codes. We are no longer just tracking weather, we are tracking a paradigm where extreme pressure deficits threaten to unleash rotational velocities that human infrastructure was never designed to survive. When the barometric floor collapses, the atmosphere compensates through violent motion. Wind is the ultimate visible manifestation of the ocean's hidden thermal energy being converted into sheer kinetic force. For decades, we have categorized this force using a framework designed in the early 1970s, the Saffir-Simpson Hurricane Wind Scale. It is the universal language of civil defense, running from Category 1 to Category 5. The top tier, Category 5, is defined by sustained winds of 252 kilometers per hour or higher. There is no upper limit. Any storm crossing that threshold is simply deposited into this final, open-ended bucket. When this scale was created, a cap at Category 5 made perfect logical sense. In the climate of the late 20th century, storms sustaining winds significantly above 260 kilometers per hour were exceedingly rare. From a structural engineering perspective, the distinction between 260 kilometers per hour and anything beyond it seemed purely academic. At 250 kilometers per hour, standard residential structures are fatally compromised. Roofs fail, masonry crumbles, and regional power grids are dismantled. The architects of the scale assumed that once winds reach catastrophic levels, more wind simply produced finer debris. Total destruction was considered a terminal state. A building either stands or it does not. But the atmospheric anomalies we are tracking today are aggressively challenging that assumption. As the ocean's deep heat reservoirs fuel unprecedented pressure deficits, the resulting winds are skyrocketing past the old Category 5 threshold. We are no longer looking at storms hovering around 260 kilometers per hour. We are documenting anomalous systems generating sustained winds of 300, 320, and even exceeding 340 kilometers per hour. At these velocities, the damage profile is fundamentally altered. Wind pressure does not increase linearly with speed, it increases exponentially. The destructive force of a 320 km per hour wind is not marginally more than a 252 km per hour wind. It is a massive leap. It is a class of kinetic force capable of overstressing high-rise steel frames, shattering impact-resistant architectural glass, and obliterating critical infrastructure engineered specifically to survive standard Category 5 conditions. This exponential leap in destructive potential has triggered a profound crisis within the global meteorological community. The Saffir-Simpson scale is being systematically outpaced by the very ocean it was designed to measure. Researchers have recently published peer-reviewed studies proposing the formal implementation of a Category 6 designation, hypothetically starting at 308 kilometers per hour. Several storms in the last decade, including the mechanical buzzsaw of Hurricane Patricia, would have easily qualified for this terrifying new classification. While agencies debate the communication merits of expanding the scale, the scientific reality is undeniable. The fact that the world's leading atmospheric physicists are seriously discussing a Category 6 tells you everything you need to know about the trajectory of our planetary system. We are attempting to contain the fury of a modern climate using an outdated ruler. The label we apply to the storm does not change its physics, but it does expose a chilling vulnerability in our preparedness. When civil defense authorities issue a Category 5 warning, they are telling the public to prepare for the worst that history has recorded. But what happens when history is no longer a reliable guide? What happens when a coastal metropolis, engineered to withstand the ceiling of the old world, is suddenly struck by a 330 kilometer per hour atmospheric anomaly from the new one? The wind is the visible edge of the blade, and that blade has never been sharper. When we discuss winds exceeding 300 kilometers per hour, it is inherently easy for the human mind to imagine a localized, concentrated event, a narrow, highly destructive vortex that obliterates one specific neighborhood while leaving the adjacent county relatively untouched. But a tropical cyclone is not a localized tornado. It is a rotating atmospheric system of planetary scale. The sheer geographical footprint of these modern anomalies is every bit as terrifying as their peak intensity. We are tracking circulatory systems with diameters spanning anywhere from a few hundred to well over 1,000 kilometers. They do not merely strike a single city, they engulf entire coastlines, placing multiple states or even multiple sovereign nations under simultaneous siege. To fully comprehend the absolute spatial limits of what the ocean can produce, we must look at the historical benchmark of super typhoon tip. While TIP established the absolute floor for barometric pressure, it also set the historical ceiling for sheer physical size. At its peak, the circulation of Super Typhoon Tip stretched roughly 1,380 miles, over 2,200 kilometers, from one edge to the other. That is a single rotating storm system wider than the distance from New York City to Denver. Its wind field covered an area estimated at over 1.5 million square miles, creating a massive footprint large enough to blanket nearly half of the continental United States. If a storm of that immense, continent-spanning scale were to strike a densely populated modern seaboard today, the outer rain bands would paralyze infrastructure and exhaust emergency response capabilities across half a continent long before the core ever made landfall. Yet the most dangerous structural evolution of a modern cyclone lies in a terrifying paradox. As the outer bands of the storm expand to cover entire regions, the inner core can violently and aggressively contract. Inside the center of a mature cyclone sits the eye, a column of descending dry air that forms only when a system reaches intense, mature organization. A standard hurricane eye typically measures roughly 20 to 40 miles across. But under the hyperfueled conditions of modern deep-water heat reservoirs, the storm compresses its core to maximize thermodynamic efficiency. The eye wall tightens, shrinking down to what meteorologists call a pinhole eye. When a pinhole eye forms, the entire destructive engine of the storm is concentrated into a ring that is under 10 miles in diameter, sometimes as small as 5. The atmospheric physics perfectly mirror the earlier analogy. Reduce the radius of rotation, and the rotational speed must violently increase to conserve angular momentum. The storm rapidly transitions from a broad circulation into a highly compressed, spinning buzzsaw. Hurricane Patricia featured an eye wall so extraordinarily compact that its entire ring of total destruction was smaller than the city of Los Angeles. This structural duality is what makes modern atmospheric anomalies nearly impossible to manage from a civil defense perspective. You are facing a sprawling 1,000-kilometer outer envelope delivering torrential, unceasing rain and sustained gale-force winds across multiple jurisdictions, systematically shutting down airports, highways, and regional power grids. And embedded deep within that massive, paralyzing envelope is a highly contracted, 10-kilometer pinhole core delivering Category 6 kinetic annihilation to whichever specific coordinates it happens to cross. The broader infrastructure is effectively paralyzed by the macrostorm, leaving the direct impact zone completely isolated, cut off, and unaided when the microstorm arrives. These systems are not just getting stronger, they are structurally adapting to inflict maximum systemic failure on a continental scale. While the sheer velocity of theoretical Category 6 winds and the massive architecture of these systems capture our immediate attention, wind is ultimately just a transfer mechanism. The true, underestimated power of an atmospheric anomaly lies in what that wind does to the ocean surface below. Waves at sea are built entirely by wind. The stronger that wind blows, the longer it is sustained, and the greater the distance of open water it travels across, the more massive the resulting waves become. When you take a Category 5 or theoretical Category 6 wind field, spinning at over 300 kilometers per hour, and drag it across hundreds of miles of deep, uninhibited ocean, you generate wave fields that no other weather system on this planet can match. Inside a mature, highly organized cyclone, the wave pattern does not simply roll in a single, predictable direction. It is fundamentally chaotic. Because the extreme wind rotates violently around the storm's central eye, the water is pushed in continuous, conflicting circles. On one side of the eye wall, the waves travel perfectly in sync with the storm's forward motion, allowing them to accumulate energy and grow to monstrous heights. On the opposing side, these newly formed waves collide violently with each other and with the storm's own movement, producing confused, highly dangerous seas capable of capsizing massive vessels. The scale of these formations defies standard human comprehension. We are not talking about large surfing swells, we are talking about moving topography. During Hurricane Ivan in 2004, a specialized research buoy positioned in the Gulf of Mexico recorded a single wave measuring an astonishing 91 feet, or roughly 27 meters. To put that into physical perspective, a 91-foot wave is the exact equivalent height of a 9-story commercial building. A decade later, during the catastrophic crossing of Super Typhoon Haiyan, satellite-based radar altimeters measured wave heights in the open ocean exceeding 90 feet. Some analytical estimates suggested the largest individual crests topped 100 feet, or over 30 meters. But the most terrifying phenomenon hidden within this chaotic environment is the rogue wave. Rogue waves are individual, spontaneous anomalies that rise significantly taller than the surrounding wave field, sometimes reaching 2 or 3 times the height of the average massive wave. They appear suddenly and without warning, usually materializing at the exact intersection point where multiple wave trains moving in different directions violently collide. Inside the core of a super typhoon, rogue waves are far more common than in normal weather, and their heights are exponentially amplified by the already massive background wave field. Imagine an environment where the average wave is 15 meters high, and suddenly, through violent constructive interference, a 30-meter rogue wave erupts from the trough. Modern global shipping infrastructure, cargo vessels, and offshore oil platforms are structurally designed to withstand wave heights of roughly 60 to 70 feet. When a storm generates rogue waves pushing past 100 feet, it rapidly exceeds the metallurgical and structural limits of the largest ships ever constructed, tearing thick steel apart with raw hydrostatic pressure. Yet the ultimate terror of these 10 to 15-story walls of water is not what they do out in the deep ocean, but what happens when they finally run out of room. As these massive kinetic batteries approach the shallow continental shelf, they do not cleanly dissipate. They ride on top of an even larger, far more lethal mechanical process. The crashing waves are merely the battering rams. They are mounted on the front of an inescapable, silent bulldozer that is about to permanently alter the coastline. When the media covers a landfalling cyclone, the camera lens is almost exclusively pointed at the sky. News networks broadcast footage of bending palm trees and shattering glass. Wind is what captures the human imagination because it is visible. Wind makes for spectacular television, but for civil defense agencies, the wind is merely a distraction from the storm's apex predator. The wind damages property, but the deadliest part of a hurricane is almost always the water. Historical data reveals a chilling statistic. The wall of ocean water pushed inland by a cyclone has killed more people in modern tropical storms than every other hazard combined. Nearly 90% of fatalities in these extreme atmospheric events are directly related to water. This phenomenon is known as storm surge, and it remains deeply misunderstood by the populations in its path. Storm surge is not a tsunami, is not a sudden, solitary shockwave triggered by an earthquake. It is a relentless, gradual rise in sea level that can extend for miles inland. It is mechanically driven by two simultaneous forces. First, the extreme low pressure at the storm center creates an atmospheric vacuum, allowing the ocean surface to physically bulge upward. Second, the sustained hurricane winds act like an invisible plow, relentlessly pushing millions of tons of water in the direction they blow. Over the deep, open ocean, this pushed water simply moves and dissipates. The danger remains entirely hidden beneath the surface. But as the storm approaches a coastline, the geometry of the ocean floor changes everything. The massive volume of water being pushed forward suddenly has nowhere to go. As it collides with the shallow continental shelf, the sloping seabed forces the immense weight of the water upward, rather than allowing it to safely spread horizontally. The ocean physically piles up against the shore. In a standard, historical hurricane, a storm surge might reach 3 to 6 meters. But in the hyperfueled systems we are tracking today, we are modeling extreme surge events exceeding 10 meters. During Hurricane Katrina in 2005, the surge reached heights of 28 feet along parts of the Mississippi coast. Structures heavily reinforced to withstand Category 5 hurricane winds were simply swept off their concrete foundations by the sheer, blunt force of the water. Most of the deaths from Katrina were caused by drowning, not wind damage. When Super Typhoon Haiyan struck the central Philippines in 2013, it generated a surge of more than 20 feet, arriving with such incomprehensible speed that over 6,000 people died, mostly drowned. A massive challenge emergency managers face today is that storm surge is exceptionally difficult for the public to visualize. A forecast of 18 feet of surge sounds abstract, almost like a mathematical theory. But translate that into architectural reality. A typical single-story house is about 10 to 12 feet from the floor to the ceiling. 18 feet of water means that the entire house is completely submerged, with an additional 6 feet of dark, churning ocean flowing above the roofline. At 20 feet of surge, even many large, two-story homes are completely overtopped. When the water arrives, it is not a clean, surfing wave. It is a rapid, unstoppable dark tide carrying vehicles, uprooted trees, and the toxic debris of a destroyed city. It bursts through impact-resistant windows and fills first-floor living rooms in a matter of minutes. People who choose to stay behind, trusting their engineered roofs to survive the wind, suddenly find themselves retreating to their second floors and then desperately breaking into their own attics to escape the rising waterline. The brutal, uncompromising reality of these anomalies is that the ocean physically relocates to your neighborhood. They do not die from the wind. They drown in the dark. When we watch a hurricane approach the coastline on radar, our minds naturally isolate it. We view it as a distinct, self-contained organism moving across a map. We assume that a cyclone is a closed thermodynamic loop, a localized machine that draws energy from a specific patch of water directly beneath its eye, churns it through its convective engine, and leaves a colder wake behind. In traditional meteorology, this closed system model dictated that a storm would inherently weaken once it moved over cooler shelf waters or made landfall. It was supposed to run out of fuel, but as we dissect the anatomy of modern atmospheric anomalies, we must discard this illusion. A tropical cyclone is not a closed system. It is a highly aggressive, open node in a much larger circulatory network. Even outside the spinning core, there is a vast invisible structure feeding the storm. A structure that stretches for thousands of miles across the ocean and the sky. To comprehend how a modern storm sustains its terrifying intensity, we must look at what meteorologists call atmospheric rivers. These are not metaphors. Atmospheric rivers are real physical structures. They appear on satellite water vapor imagery as long ribbons of high water vapor in the lower troposphere flowing from the tropics toward higher latitudes. They are invisible to the naked eye, but instruments that measure water vapor see them clearly. The scale of these celestial waterways defies our terrestrial understanding. The largest of these rivers can carry more water in vapor form than the Mississippi River carries in liquid form. Satellite-based measurements from NASA and NOAA moisture monitoring instruments have shown that during peak typhoon season, the atmospheric river feeding the western Pacific can transport water vapor at rates equivalent to 200,000 cubic meters per second. That is more than 10 times the flow of the largest rivers on Earth. When a tropical cyclone forms over warm water, it immediately begins to feed on the moisture available nearby. But the storm is not a closed system. Air spirals into the center from hundreds of miles away, and that inflowing air carries moisture with it. If the broader atmospheric environment contains an atmospheric river, the storm taps into that flow. It is exactly like a wildfire sitting next to a pipeline of fuel. The storm draws from the river, intensifies, and in turn pulls the river further inland as it moves. This open system connection completely bypasses our traditional defense mechanisms. A hurricane moving toward a coastline may appear to weaken as it crosses cooler shelf water near shore. But if an atmospheric river is still feeding it from the tropics, the storm could hold its intensity or even regain strength right before landfall. A cyclone that finds itself inside an atmospheric river can sustain itself even over slightly cooler ocean because the moisture supply coming in from elsewhere keeps its heat engine running. When these systems finally cross the shoreline, the true horror of the atmospheric river is unleashed upon the interior. A hurricane that moves inland and stalls over land continues to draw moisture from the river behind it. Rain falls for days, rivers flood, and mountains receive more water than they can channel. The storm itself is weakened in wind, but the flood continues. The sky is not an empty backdrop, it is a fluid delivery system. We live in an era of unprecedented observational supremacy. Above our heads, geostationary satellites positioned 36,000 kilometers above the equator provide continuous imagery of tropical regions. Polar orbiting satellites slice across the sky, analyzing temperature profiles and wind vectors. On Earth, supercomputers process billions of calculations per second, running complex algorithms to simulate the future state of the atmosphere. This technological arsenal grants us a comforting, yet profoundly dangerous, illusion of total control. We look at our screens, see the swirling clouds, and believe we have mastered the mechanics of the ocean. But observation is not prediction. And in the face of these new atmospheric anomalies, our foundational forecasting architecture is beginning to fracture. To understand why the system fails, you must understand the dichotomy of modern meteorology. Forecasting a tropical cyclone is fundamentally divided into two distinct disciplines: predicting the track and predicting the intensity. When it comes to the track, the physical path the storm will carve across the ocean, our computer models are remarkably accurate. We understand the macro-level atmospheric steering currents, the high-pressure ridges, and the global winds that push the cyclone forward. With high confidence, emergency managers can plot the trajectory days in advance. We know exactly where the monster is walking, but when it comes to predicting how strong that monster will be when it finally arrives, our technological supremacy collapses. The terrifying problem for modern meteorologists is that rapid intensification remains incredibly difficult to forecast accurately. While we can pinpoint a landfall location within a few miles, our intensity forecasts routinely carry a lethal margin of error. It is now common for operational models to underestimate a storm's peak wind speed by 30 to 80 kilometers per hour within a critical 24-hour window. Why does a supercomputer fail to see a theoretical Category 6 hurricane forming? The answer lies in the mathematical architecture of the simulation itself. Global weather models divide the Earth's atmosphere into a digital grid. However, the exact physical processes that trigger rapid intensification, the sudden transfer of heat within the eyewall, the contraction of a pinhole eye, happen on scales far smaller than the grid resolution of most operational weather models. The simulation is simply too coarse. By the time the computer model finally recognizes that the pressure is plummeting, the system has often already done most of its explosive strengthening. Forecasters relying on these model outputs can easily find themselves issuing warnings that dramatically underestimate a storm's true intensity at landfall. This is the nightmare scenario for coastal emergency managers who desperately need accurate timelines to execute mass evacuations. Hurricane Otis in 2023 stands as the absolute, tragic proof of this technological blind spot. Otis strengthened from a moderate tropical storm with 65-mile-per-hour winds into a catastrophic Category 5 hurricane with winds of 165 miles per hour in just 12 hours. Most forecasts had predicted a much weaker landfall. The city of Acapulco went to sleep expecting a manageable rain event and woke up to an apocalyptic buzzsaw. Because the models failed to resolve the explosive deepening over the deep water offshore, there was almost no time for the city to prepare. We have built our defense strategy on the assumption that supercomputers can simulate nature perfectly. But the ocean is now operating outside the historical parameters those computers were trained on. The terrifying reality of modern disaster management can be distilled into a single, undeniable truth that we can predict where the storm will go. We cannot predict how strong it will be when it gets there. When a forecast fails spectacularly, or when a storm shatters a historical pressure record, our natural psychological defense mechanism is to label it a freak event. We call it an anomaly. An outlier, a once-in-a-century statistical ghost. This terminology is deeply comforting because it implies that once the disaster passes, the atmosphere will naturally return to stable, predictable equilibrium. But to view these modern storms as isolated anomalies is a fundamental failure of atmospheric comprehension. Step back from the individual storm tracks. Step back from the pinhole eyes and the 300-kilometer-per-hour wind fields. What emerges is not a random catalog of disconnected outliers. Is a highly consistent, terrifyingly clear planetary signal. The foundation upon which all our meteorological models were built is physically shifting beneath our feet. The global ocean, the thermal engine of our planet, is fundamentally warmer than it has been in human history. Over the past century, the average global sea surface temperature has increased by roughly 0.6 to 0.8 degrees Celsius. To the layman, a fraction of a degree sounds completely inconsequential, like a mere statistical rounding error. But in the realm of thermodynamics, water requires an immense amount of energy to heat. To raise the temperature of the top layer of the entire global ocean by even half a degree requires the absorption of a staggering volume of thermal energy. We are talking about the equivalent of billions of atomic detonations trapped within the water column. That energy does not just sit idly in the dark. It constantly seeks a release mechanism. Tropical cyclones are the Earth's primary method for venting heat from the equator toward the poles. As this thermal baseline rises, the behavior of the venting mechanism fundamentally changes. The total number of tropical storms forming each year might not drastically multiply. However, the distribution of their intensity is violently shifting toward the extreme end of the spectrum. The probability of a tropical cyclone reaching major hurricane status, defined as Category 3 or higher, has increased significantly across multiple ocean basins over the last 4 decades. We are witnessing a disproportionate surge in Category 4 and Category 5 events. The storms are responding exactly as the laws of physics dictate. Warmer sea surface temperatures provide more fuel. Deeper warm water layers extend the available energy reservoir. Higher atmospheric humidity means more moisture can feed into the storm. Every single environmental factor that contributes to cyclone intensification is aggressively moving in a direction that favors extreme outcomes. This brings us to the most chilling realization of modern climatology. The marine heat waves, the deep warm water reservoirs, the shattered barometric floors, these are not temporary deviations. The ocean is not returning to its previous equilibrium. It is settling into a new, significantly warmer baseline. Therefore, the storms generated by this new ocean are not anomalies. They are the new standard operating procedure of the planet. When we continue to use the word unprecedented, we deceive ourselves into thinking we are experiencing bad luck. We are not experiencing bad luck. We are experiencing a newly calibrated thermodynamic engine operating at a higher RPM. The theoretical ceiling on storm intensity is continually moving upward. The environment is not broken, it is simply adapting to a massive influx of trapped heat. The planet is finding a new balance, but that balance requires atmospheric violence on a scale that human civilization has never been forced to endure. We have established that the planetary baseline is permanently altered. The ocean is retaining a catastrophic volume of thermal energy, raising the theoretical ceiling for storm intensity across the board. But this trapped heat does not distribute itself evenly across the globe. It pools. It shifts, and its release is governed by a massive, cyclical mechanical system operating deep within the equatorial Pacific. To understand exactly when and where the next atmospheric anomaly will strike, we must examine the planetary master switches. We must look at the El Niño Southern Oscillation. For decades, the public has been conditioned to view El Niño and La Niña as relatively benign, naturally occurring weather patterns, a convenient explanation for a wet winter in California or an unusually dry summer in Australia. But in the era of a hyperheated ocean, this fundamental misunderstanding is profoundly dangerous. These are not merely seasonal weather patterns. They are the primary biological rhythms of the Earth's thermal engine. They dictate exactly how, when, and where the global ocean chooses to vent its newly acquired, massive heat reserves into our lower atmosphere. In a neutral state, the Pacific Ocean, the single largest body of water on Earth, operates under a stable regime of trade winds constantly pushing warm surface water toward Asia. But when this physical system breaks down and flips into an El Niño phase, the trade winds collapse. Millions of square miles of superheated water forcefully slosh back toward the Americas. This is not just a localized oceanic event, it is a profound, violent alteration of the entire global atmospheric circulation. The jet streams physically relocate. The atmospheric rivers are aggressively rerouted. And the global wind shear, the primary atmospheric defense mechanism that tears developing hurricanes apart, is fundamentally altered across the hemispheres. Conversely, during a La Nina phase, the trade winds hyperaccelerate. The warm water is violently compressed against the western Pacific, creating an immense thermal powder keg, while simultaneously erasing the protective wind shear over the Atlantic basin. La Nina acts as a master switch that turns the Atlantic Ocean into an uninhibited, frictionless corridor for rapid intensification. What used to be a reliable natural cycle of alternating regional risks has now been warped into a mechanism of extreme, polarized atmospheric violence. The terrifying reality we are tracking today is that the rising thermal baseline we discussed in the previous chapter is essentially injecting steroids into this cyclical pendulum. We are no longer experiencing standard, predictable oscillations. We are increasingly witnessing super El Niños, followed immediately by relentless, multi-year, triple-dip La Ninas. The pendulum is swinging wider, faster, and with infinitely more destructive kinetic energy than our historical records can account for. This extreme cyclical amplification completely blindsides regional preparedness and human psychology. A coastal population might experience a quiet, dormant hurricane season during a strong El Niño, lulling civil defense agencies and local residents into a fatal false sense of security. Emergency budgets are quietly cut. Evacuation plans collect dust. The public subconsciously believes the threat has permanently diminished. But the thermal energy has not disappeared. It is simply being stored, actively building pressure, waiting for the pendulum to swing back. When the cycle inevitably flips to La Nina, the Atlantic basin does not just gradually return to normal, it detonates. The switch is thrown, the protective atmospheric shear vanishes overnight, and populations that have not seen a major storm in a decade are suddenly staring down multiple Category 5 anomalies in a single month. These oscillation cycles are the ultimate, invisible orchestrators of chaos. They take the slow, steady accumulation of global heat and concentrate it into highly focused, hyperdestructive seasonal windows. We are strapped to a planetary machine where the gears are slipping, the engine is running far too hot, and the switches are flipping with unprecedented, violent unpredictability. We have traced the anatomy of the modern anomaly from its genesis in the deep, superheated reservoirs of the ocean to its catastrophic termination against the fragile architecture of human coastlines. We have seen how the traditional metrics of meteorology, the historical baselines, the thresholds for rapid intensification, and the Category 5 ceiling have all been systematically dismantled by a thermal engine operating at unprecedented capacity. The evidence is not anecdotal. It is a continuous, irrefutable data stream pointing toward a singular, terrifying conclusion. The planetary system has permanently outpaced our predictive models. For half a century, civilization treated extreme weather as a solvable equation. We built a massive infrastructure of supercomputers and orbital sensors based on the assumption that if we gathered enough data, we could anticipate the ocean's next move. We believed technology would buy us the ultimate defensive resource, time. Time to evacuate, time to survive. But the physical reality of the ocean has broken that equation. When a storm can explode from a disorganized depression into a Category 6 kinetic buzzsaw overnight, the technological supremacy of our satellites becomes irrelevant to the people in its path. When deep water heat content is so vast that storms no longer weaken before landfall, but accelerate right up to the shoreline, the standard 48-hour evacuation window ceases to exist. We are watching the complete collapse of the proactive defense paradigm. This leaves us standing at a profoundly dangerous crossroads. The infrastructure we rely on, the concrete seawalls, electrical grids, and drainage systems, was engineered for a climate that no longer exists. It was built to withstand the historical maximums of the 20th century. But the ocean is no longer bound by those limits. It is generating massive wave fields and 30-foot storm surges that effortlessly overtop our civil defenses, turning the structures meant to protect us into inescapable traps. The global response to this escalating threat has been dangerously sluggish, paralyzed by a collective psychological refusal to accept the new baseline. We continue to debate the semantics of anomalies, while the physics of the atmosphere visibly rewrite themselves on our radar screens. We are attempting to manage a Category 6 reality with a Category 3 level of preparedness. To survive the coming decades, a radical shift in our civil defense philosophy is a strict biological imperative. We can no longer afford the luxury of assuming we will see the worst coming in time to get out of the way. The era of comfortable meteorological lead times is officially over. The assumption of safety based on historical precedent is now a lethal vulnerability. We must engineer our cities not for the storms we have recorded in the past, but for the theoretical maximums the new ocean is mathematically capable of producing today. Until we accept the uncompromising violence of this shifting planetary foundation, we will continue to be blindsided. We will continue to watch in horror as the computer models fail, the coastal waters rise, and the evacuation time runs out. The ocean does not negotiate. It does not care about our forecasting limits or our building codes. It only responds to the immense thermal energy it has been forced to absorb. We built our modern world on the comforting promise of predictability. But the data flashing on the screen is clear, and the wind outside the window is rising. We are no longer predicting storms. We are reacting to them.